All right, so here in class we talked about atomic radius and ionization energy. Then that filled out all of our pages 2 and 3. We're actually going to look a little bit at 4, but there's nothing that you need to write there or do there. So this is just a recording to help you catch up or revisit these notes on these first two trends. So first, I know the first thing you see on that page is a big old periodic table. We're going to come back to that. That's going to be our main focus for how to kind of do these trends using elements, but first we need to understand a little bit more context. So what is atomic radii or radius? It is the average distance from the center of the nucleus to the edge of the electron cloud. This is basically the definition of a radius, which is, for circles, center to the edge. But since we're talking about atomic radii, it's just a special type of circle. It's the center of the atom, center of that nucleus, to the edge of the electron cloud. Now, as fancy as this definition is, and you should recognize this on a test or a quiz, because these are the words I'll be using there, really when it comes down to it, we use a radius to measure the size of a circle. So this atomic radius is really just all about the size, the relative size of our atoms. Now, the size of our atom is going to be affected by those two properties that we defined at the end of our first podcast, nuclear charge and shielding effect. So this is not where we're going to define and explain what those trends are. I will start with a short explanation. This little red thing reminds us that nuclear charge increases as we move from left to right across a row. And this is literally the charge of our nucleus. So I'm touching on that here. You may or may not want to write down that red stuff, but really what we're focused on here is how does that nuclear charge affect the size of our atom? Because all of our trends, atomic radius included, can be explained with one or both of these two effects. So if we start with nuclear charge, like I just said, nuclear charge is about the strength of our nucleus, the pull of our nucleus, the total charge of that nucleus with all of its protons. So as that nuclear charge increases, as our nucleus gets stronger, it's pulling harder and harder on the electrons. As we're adding more and more protons to that nucleus, they are pulling harder and harder. Now, yes, we're adding more electrons, but those electrons are being added to the same energy level. So we're looking at a specific element, and as we add more protons to the nucleus, we're adding more electrons around the outside, but because those electrons are being added to the same energy level, they're not getting any farther away. So they're subject to feeling that pull of the nucleus. So it's really just the fact that the nucleus is getting stronger that's affecting our size. So think about it as a person standing, maybe they have a rope tied onto an electron or something. The stronger that person is, the harder they can pull on that rope, what's going to happen to the object that it's tied to? If it's anything that's movable, the stronger that person is, the stronger that pull is, and the closer that object is going to be pulled, which means the radius between that object and the person pulling on it is going to decrease. And that's what's happening with our electrons in our nucleus. As the nucleus gets stronger, it pulls those electrons in closer. So as we move across a row, from left to right in a row, our atomic radius gets smaller. Now with the shielding effect, remember this is the fact that as we go down a column, and this is always moving from the top to the bottom of a column, our shielding effect increases. And that's the idea that as we add energy levels, we have more of this protection from this. An electron on that third level has the first and the second energy levels protecting it from the pull of the nucleus. So if we're talking about that shielding effect, because the electrons are being added to those higher energy levels, and like you saw in my little drawing right there, those higher energy levels are already larger, making our atom bigger. But with that added shielding as well, that protects the electrons from the pull of the nucleus, those electrons can spread out a little bit more. And that, in addition to the extra energy levels, will make our atomic radius bigger. So as we move from top to bottom in a column, the atomic radius gets bigger. So you might want to pause this here to finish any of this writing that you need. Remember, the purple stuff you got to write down. Red stuff probably don't need, but you could. And I think that blue definition is a lot easier to remember. That's kind of the workable definition here. So we're going to summarize these trends on that periodic table that goes with our atomic radius. And like we said before, in a row, that nuclear charge getting bigger makes our radius smaller. So if I was to draw an arrow towards the biggest elements in any row, it'd be pointing to the left, because as we move to the right, our atoms get smaller. If we were going to draw a vertical arrow pointing towards our biggest elements, it would have to point down, because as that shielding increases, as we get more energy levels, our atom gets bigger as we go down the periodic table. And if you put these two arrows together, the farthest left element and the farthest down is francium. And so instead of remembering these two separate arrows or all of that complicated explanation with nuclear charge and shielding effect, all we really have to remember for atomic radius, be able to answer 90% of the questions on our test, is that francium has the biggest atomic radius. So the closer we are to francium, the larger that atomic radius is. And I kind of like this similarity here, that the largest AR, if we abbreviate atomic radius as AR, is biggest at FR. It kind of has a nice little kind of parallelism there. AR is biggest at FR. So in all of these examples down at the bottom of the page, all we've got to remember is that our francium is our largest atomic radius. So I've highlighted francium in red, and every time we look at one of these pairs of elements, Li and F, I've highlighted them here in my periodic table. It's asking us which one is larger. It's going to be whichever one is closest to Fr, which would be lithium. When we're comparing tin and strontium, strontium is a lot closer, so it's bigger. Looking at our next set of elements, sodium and rubidium, rubidium is closer, so it is larger. Most of the time, your questions are going to be at this level, just which is larger, which is smaller, or maybe like these next couple, put them in order, increasing size. You're not generally going to have to explain why. So all of that stuff we just wrote down about nuclear charge and shielding effect, 99% of the time, we don't need that. But there will be one question on your test where I'm going to tell you something like, rubidium has a greater atomic radius than sodium. Explain why. And that question is going to be worth 3 to 5 points. But that's the only time we're ever going to ask you why and have points based off of that. So like I said before, most of what you need to remember is that francium's the biggest for this trend. All the other trends will have their own unique element you've got to remember. But as long as you can remember that element, that getting closer to that element makes it bigger, farther makes it smaller, then we can do this pretty easily. So as we move down to increasing size, sometimes people make little mistakes. Increasing means getting bigger. That means that we need to be going from our smallest element to our biggest element. And because the closer we are to FR, the bigger we are, that means that we kind of need to be going from the farthest elements to the closest elements. So I know that seems pretty basic, and some of y'all are like, well, duh, why is she even writing that and saying that? Because it's so easy to get the chemistry right once you get used to it and make a simple mistake. Oh, increasing, you're thinking big. You go big to small instead. Even if you knew all the chemistry, you get everything wrong because everything is backwards. So take a second. Never be embarrassed to write this down, because even Mrs. Gunter writes this down to make sure we don't make silly mistakes. So for these three elements, we're going from far to close. So that's going to be CD, and then TC, and then Y. Looking at our next set of elements, they're all in that same column, makes it pretty simple. Farthest to closest is still the way we do it. So BE, MG, CA. Happens to be the same order they were given in. It doesn't happen often, but don't be too afraid of that happening to you. Most of the time, if people are going to just guess, they mix them up into some kind of order. Most people wouldn't guess to just leave them in the same order. But if we look at the elements in that next set, they're also pretty close together, just on that opposite side of the periodic table. Still doing small to big, increasing size, so we're going to write them in the farthest to the closest order. which means Xe, I, and Te. So hopefully that this kind of 99%, the bulk of what we're doing this unit, really is just that simple. So on the next page, we're going to talk about ionic radii, which are similar to atomic radii. Remember, ions are atoms that have gained or lost over some number of electrons. So ionic radii are the size of an atom that has gained or lost electrons. Just, a variation of that atomic radii trend. Now, there are two different types of ions, and they're going to be different sizes. Positive ions, which FYI tend to be our metals, tend to lose electrons. To be positive, you need less of that negative electron stuff. And losing electrons, just like when people lose weight, makes you smaller. Negative are the opposite. To become negative, which tend to be our nonmetals, they had to gain electrons to become more negative. And because they gain some electrons, then they are getting larger. Now, if we're comparing positive stuff to negative stuff, positive is going to be smaller than negative. But sometimes we're going to compare positive stuff to other positive stuff. And as long as the element is the same, the more negative it is, the larger it is, because those elements have gained more electrons. The more positive it is, the smaller it is, because those have lost more electrons than the ones with the smaller charge. So if we look at our examples here, magnesium and magnesium plus 2. Remember, more negative is the larger elements. Neither of these are negative, so we kind of have to think more negative or less positive is our larger radius. So Mg plus 1 is the less positive element, so it's larger. Here with our two carbon atoms, the negative one is the one that gained electrons, so it's going to be larger. So you go ahead and circle which of these fluorine atoms you think would be larger. And we'll move on to ionization energy. Once again, we're going to start with these definitions, these properties, and then start to kind of zoom out into the periodic table, the big overall pattern that we need to remember. So what is ionization energy? It is the energy required to remove or ionize an electron from an atom. And technically, it's the outermost electron from the atom. So it's not the happiest of analogies, but I kind of think of this, electrons are a lot like kindergartners. They're not really people, they don't have personalities, they're just big bundles of energy that go running around in random places and you can never really predict their behavior. So if our electrons are kindergartners, then the nucleus is kind of like their teacher, their wrangler, the person holding them together, making them, one cohesive unit. Otherwise, they'd just be everywhere. So in terms of ionization energy, this is the amount of energy a student needs to, or a kindergartner needs to use in order to escape from that teacher, escape from this atom, to go run off. Let's say they're on a field trip. So this is a teacher with a group of kindergartners at the zoo. So how much energy does that kindergartner need to use to run off and go play around at the zoo on their own? So keeping that in mind as we discuss this nuclear charge. Remember, nuclear charge is the pull of the nucleus, the strength of the nucleus, which in our analogy is the teacher, and that's going to increase as we go across a row. So as we're going across a row, as that nucleus, our teacher, is getting stronger, it's pulling harder, holding tighter to those same kindergartners, what's going to happen to the amount of energy it takes for a kindergartner to go running off and escaping? Well, the stronger that teacher is, the more control she has over the class, the more energy that student's going to have to use to escape. Then, down to like if there were 2 students with her, she's got a really firm hold on both of them. She can have her hands on both of their hands, and they're going to have to physically pull out of her grasp to escape. So, with increasing strength of our teacher, the electrons kind of have to be stronger in order to be able to escape. They have to use more energy to escape and ionize that atom. And the same is true with our electrons. In terms of shielding effect, remember that's the protection that rows and energy levels provide those outer electrons from the pull of the nucleus. So think of this like a bigger class that has rows and rows and rows of students. This one teacher is taking 50 kindergartners to the zoo. Well, that outermost kid that's trying to escape and go run off and play on his own has layers of protection. He might even be able to hide behind another student where the teacher can't even see him as he's running off and escaping or ducking behind a column or something. So as there's more and more shielding, as we have more and more layers to our electrons in their electron cloud, their electrons are more protected from the pull of that nucleus, which makes it easier for them to escape. It means that they are going to have a lower, decreased ionization energy the farther they get from the nucleus, the more shielding that they have. So for this trend, as we go across a row from left to right, our ionization energy gets bigger because we're having to pull off of a stronger nucleus. As we go from top to bottom, our ionization energy decreases because it's easier to pull our electrons off of bigger groups and bigger atoms. So if we summarize that on our periodic table, our ionization energy gets bigger as we move left to right. It gets smaller when we go down, which means our arrow should point to the top of every column. Notice how these arrows are the opposite of our atomic radius arrows. So this trend is the opposite of that trend. As our atom gets bigger, the ionization energy gets smaller, because the bigger the atom, the easier it is for those electrons to come off. Francium, honestly, just kind of loses track of electrons. It might not even realize that it's lost an electron until later on. It's just got too many of them. So if we summarize all of this down to a single element, helium is at the top right. So He has our biggest IE. Helium has our biggest ionization energy. So a lot like what we were doing, sorry about that. A lot like what we were doing with francium with our last trend, with our ionization energy, we just have to remember helium is the biggest of this trend, and then the closer we are to helium, the larger that ionization energy is. So let's go through these examples. If we look at each of them, N and O, which one is closer to helium? That's going to be oxygen. We've got Ne, F, and Cl. Which one is closest? Neon. When we've got N, As, and F. So these are not in a nice, neat, ordered row or column, but they're kind of both in each. We still just have to look which one is physically closest to He, and that's F. So hopefully the process for answering these questions, I know I didn't have any put these in increasing or decreasing order, but it's the same process as with atomic radius. We just have to remember the different element for it. Now I do want you to take a brief look at page 4. Like I mentioned before, there's nothing you need to write here at the top. You could write down these green numbers and these arrows here, but this is not something I'm going to test you on. But this is kind of a preview. Some people have asked me, how is AP Chemistry different? Is that something I could be in right now? The answer is kind of no. It's a level 2 chemistry class where we go a little bit deeper into some of the same topics that we learn about here in honors and just understand them at a more holistic level. And so our periodic trends is one of those times, and it does get more complicated, but when it comes down to it, we just go a little farther. So something you might have noticed, especially if you did that analyzing periodic trends activity with us together in class, is that the ionization energy is there's not just one for every atom. It's technically called the first ionization energy, and you might have seen that on ptable.com because we were looking at ionization, first. And if you accidentally clicked on first, you saw there was a drop down to second, third, fourth. There are more than one ionization energies for any element because they have more than one electron. So the first ionization energy is the energy to pull off the first electron. The second ionization energy is the energy to pull off the second. And all I want to point out to you is that as the number of electrons that is pulled off increases, then so does the amount of energy to remove it. That's really the only thing that most of us at the honors level need to be aware of. But, kind of fun fact, we can use those energies, and specifically the difference between the energy values, because these are the actual ionization energies down here. We can look at how those values change. So what I've done here is subtract these two numbers. From the first to the second ionization energy, it increases by 712. from the second to the third, it increases by 6,000, over 6,000. Even when we go from the third to the fourth ionization energy, that only increases by a little less than 3,000. So the fact that that jump from the second to the third ionization energy is so big tells us that we're making the jump into some of what we call core electrons, meaning they're not on that outer valence energy level. So we can actually use this to identify how many valence electrons an element has. Now, you're probably not surprised. Magnesium is in the second column. It has 2 valence electrons. But we can actually use this, and let me show you an example. We can use it to experimentally determine the number of valence electrons. This is an AP chemistry question that was on an AP exam. And it basically just tells us we've got an unknown element with these 4 different ionization energies, and then asks what family in the periodic table does it belong to. Well, because here we can see that we went up by around 900, and then we went up by like 1,200. Even this jump only went up by like 3,000. So because that second jump from the second to the third ionization energy was so big, that tells us this just had 2 valence electrons. Everything else was core electrons, which means it has 2 valence electrons. This element is going to belong to that alkaline earth metal family, just like the magnesium did up above. So I think it's cool. And like I said, it's the same chemistry. We'll just take it a little bit farther in AP. So the rest of page 4 was some practice problems. We probably only had 5-10 minutes in class to look at these. But if you did miss class, if you are feeling like you're behind and needing to catch up, go ahead and give these a try. 5 and 6 are a little bit, they get a little more complicated, especially parts B and C here. So if you don't feel comfortable with those, maybe just try and get a head start on this stuff. Next class, we're going to be spending practicing. It's mostly going to be pages 7 and 8 in class, but we can find some time to finish up page 4. But that top questions 1 through 4 are really simple and straightforward. So if you have the time, this is a short unit, so whatever you need to catch up on and be proactive about would be great.